today we're going to cover sections 15.1 and part of 15.2. Just for an opening problem, I thought I'd see can you do this one. Doesn't even have the right number of digits down here, does it? What we want to do is some out-of-the-box thinking. How can I make this work in a different way than usual? You want to turn your player off and think about it for a second. Here's the answer. Just look in a mirror. There it is, 9, 1 and 8 is 18, right? Alright, so much for that one. Today, our topic is going to be an out-of-the-box topic. A little different way of thinking about integration. We're going to do integration in two variables. You did this in Calculus 1, right? This is what you did. You said to find the area under a continuous curve, y equals f of x, or you can do some other cases, piecewise continuous, for instance, where for simplicity we'll suppose f of x is non-negative, stays on or above the x-axis. Suppose I want to estimate that area. What did I do in Calculus 1, right? I took the interval from A to B, where I wanted to find the area below the curve, and I broke it up into n subintervals, from x0 to x1 to x2 up to xn is equal to b and x0 is equal to a. Then I call this width delta x1 is x1 minus x0, delta x2 is x2 minus x1. I broke this up into n subintervals. They don't have to be equal width in general, just so long as you break it up into n intervals, you can call it an estimate, right? And you say, well, the area of each rectangle, say the kth rectangle, is delta xk as the base, times f of xk star. You take xk star any point in the kth interval, and you take the height of the function, f of xk star, right there. And so you take that height for the function, for the rectangle, f of xk star, and this width, delta xk, base times width, height times base, let's say f of xk star, lift the star up, times delta xk, is the area of the kth rectangle. Then you sum over n rectangles, the area of each, and you get the sum of these rectangle areas, estimating the area of the curve. And what you found was that you could use inscribed rectangles, where you took maybe the height at this point, on the left here in this case, and the same base, and inscribe each rectangle, underestimate the area on each interval, add all those up and get an estimate for the area of the curve. Or you could use circumscribed rectangles, where you take the height of the rectangle, say in this case at the right end point, and you overestimate the area of each rectangle. And guess what happened if f is continuous, or some other nice functions? Then n is the limit. As n went to infinity of the same sum, it didn't matter how you partitioned this, as long as the width of the widest subinterval went to 0 as n went to infinity. That's implicit in this notation here. You got the same number. For a continuous function, and some other nice cases, the limit of this sum is the same number whether I inscribe and underestimate on each interval. I add this up and I get some number. If I circumscribe, overestimate each interval, and take the limit is the same number. We ought to call that the area under the curve, we said. So that in Calculus 1 is how you define the definite integral, right? You said that the exact area of the curve is the limit as n goes to infinity of the sum of n rectangles of height f of xk star delta xk. We'll just define the area that way, and because that's such a useful quantity, we'll also call it the definite integral. Integral from a to b f of x dx will mean the limit of the sum, right? Now what can we do analogously in Calculus 3 when we have a function of two variables? Now we're interested in finding the volume below a continuous surface, z equals f of x, y, or some other nice thing. Maybe it's a finite number of nice pieces stuck together. And suppose, again, f is greater than or equal to 0, so this sits over the xy plane. And we'll estimate the volume over each subrectangle. We'll take a rectangular region over which the function is defined, break it up into n rectangles. We can partition capital M intervals in this direction, capital N intervals in this direction. We have m times n equals little n subregions over which we're going to any rate to estimate the volume below a surface now when we have z equals a function of x and y. So we can estimate it by adding up these little rectangular box volumes, and the sum of the little n volumes of all these rectangular boxes will estimate the volume below the surface and over the xy plane. Now, each box looks like this. We can take any point whatsoever inside the kth box, let's say, or jkth box, xj and yk it says here. xj star, yk star, I'll take the height of the rectangle at that point, maybe the middle of the box I show here, and I'll go up to the surface of the middle of the box. I'll make a box that's the height of the surface at that point, and say, what's the volume of that box? Well, it's delta xjy, that's the width of the jth interval in the x direction, delta yk long, that's the width of the interval, the length of the interval in the y direction. Width times length times the height, f evaluated at some point, whatever you want in that little rectangle here, gives you the volume, right? Base, width times length times height is the estimated volume under the surface. The exact volume of this rectangular parallelepiped is what we technically call a rectangular box. So here's the estimated volume under the surface. We sum height times width times length over n subrectangles. Now what happens if f is continuous, or some other nice cases, the limit of this estimating sum, I put k equals 1 to n here, we can also sum over both indices, it's the same thing. I should have put j equals 1 to m and k equals 1 to capital N here. It's like this one. So this, call this one the volume, the estimated volume. Then if you take the limit as the number of rectangular boxes goes to infinity, of the sum of the volumes of the boxes, that gives you the same volume, same number, no matter how you partition these two axes, as long as the width of the widest sum interval in both directions goes to 0 as n goes to infinity, and f is continuous. Now, whether or not f was non-negative in calculus 1, we still define this to be the definite integral, the limit of the sum f of xk star delta xk. We define that to be the definite integral from a to b. And we just said, well, if f is negative, then this is actually minus the height of the rectangle times the width. So we're adding up minus the area of the rectangle, so we get minus the area of the curve. So we'll define the definite integral this way regardless in calculus 1. And say, well, if f is negative on the integral, this gives us minus the area above the curve, area being non-negative always. And if f of x is non-negative, then we can say this is the area below the curve and over the x-axis. Similarly, we're going to define the definite integral, double integral, as the limit of, that we just wrote, of the sum of the rectangular box volumes. And if f is negative, this will be a negative times a positive will give us minus the volume below the xy plane. And if f is positive, or non-negative, we'll say this is actually the volume over the xy plane and beneath the surface. But in any case, we'll define the double integral to be this. And this will always exist when f is continuous over a rectangular region going x going from a to b and y going from c to d. If this integral exists, we'll say that f is integrable over the rectangle R. That's another definition. And then the question becomes, how can I evaluate it? Well, we have some nice theorems. For instance, the sum and difference of double integrals. If the two individual functions are integrable, the integral of the sum or difference is the sum or difference of the integrals. You can break it up into two double integrals, just like you could in calculus. Or you can pull a constant out of a double integral, just like you could out of a single integral in calculus 1. Then finally, to evaluate a double integral, well, we don't have the fundamental theorem of calculus anymore, right? That was for single integrals. We could take an antiderivative at b minus an antiderivative at a. The same antiderivative A, and that would give us the value of the definite integral defined as the limit of that sum. That was the fundamental theorem of calculus, right? That's how you actually evaluate them. What shall we do for double integrals? If it's over a rectangular region R, we use Fubini's theorem. We say that if f is continuous over a rectangle, x going from A to B, y going from C to D, then what we know is its integral exists. It's equal to the iterated integration in either order, like this, where these are calculus 1 integrals. So you have an inside integral from A to B of f of x, y dx, which is a partial integral. Like partial derivative, you treat the other variable as constant. So on the inside integral, I treat the outside variable y as a constant due to this calculus 1 integral. That's a partial integral. And then I get a function of y only, and I just do the regular calculus 1 integral on the outside. We'll do an example in a minute. Or we can do it in the other order. We can integrate y in the inside, treating x as a constant, and then integrate with respect to x, the function of x that results. So that's Fubini's theorem, how we can evaluate double integrals over a rectangle. We can just do an iterated integral between the endpoints in the x direction and endpoints in the y direction. With the inside integral, a partial integral. So here's an example. Let's first do an example of a estimating sum instead of applying Fubini's theorem right off. Let's say, suppose I want to evaluate the Riemann sum, we call it, that either that single sum from calculus 1 or this double sum we're just writing that estimates the area over the volume, we call a Riemann sum. If we compute the Riemann sum corresponding to this double integral, which is the limit of the Riemann sum, let's say over the rectangle from 0 to 1 and 1 to 3, using this grid below. Suppose this is my rectangle in the xy plane, and I want to integrate the function 2x plus y, that is the volume below the surface z equals 2x plus y, over this rectangle in the xy plane. I didn't draw the three-dimensional picture on this one. And let's use the center points of each rectangle to take the height of the surface, 2x, z equals 2x plus y. Right? Then the Riemann sum is just without the limit, sum j going from 1 to m, k going from 1 to n, where I partition the x-axis into n intervals, 1, partition the y-axis into n intervals, 2, and I take height times width times length. This is the volume of the kth box. Now there's only two of them though. There's only two subrectangles for the rectangular region. I picked myself a really easy case. It'll be harder on your homework. But I have two rectangles, so j goes from 1 to 1 and k goes from 1 to 2. So I have f at x1 star, y1 star, delta x1, delta y1 when j equals 1. And then I let k equals 2, and I have f of x1 star, y2 star, delta x1, delta y2 is the sum of the volumes of the two rectangular boxes that sit over these two rectangles in the xy plane. And what are they? Well, f, the function I'm integrating, is 2x plus y, so I just, and I take center points here. So I'll take x equals 0.5, y equals 1.5, the center of this box. So I take f at that point for the height of the first rectangle times its width is 1 by 1 here, the way we've drawn it. And then plus the height of the rectangle f at 0.5, 2.5, that's this center point, right? 0.5 and 2.5, times width 1 times height, length 1. And we just have to add those together. Well, f is 2x plus y, so we take 2 times 0.5 plus 1.5, 2 times 0.5 plus 2.5. And now we add all those numbers together, we find out that 6 is the estimated volume below this plane, z equals 2x plus y. And actually, if you work out the integral, you might be surprised to find that's actually the exact value. Turns out, when you use center points like this, this estimating sum gives you the exact volume below, because it turns out when you're below the surface, the area you lose exactly cancels the area you gain when you're above the surface with the rectangle. This actually gives us the exact result for linear functions, ax plus by plus c, turns out, but we haven't proved that. So there's an example, though, of estimating the volume under this plane, z equals 2x plus y, and over this rectangle in the xy plane. Now let's try something more interesting. Suppose we want to find the volume below the surface z equals e to the x cosine y over this rectangle. X goes from 0 to 1, y goes from minus pi over 2 to pi over 2. And this time let's find the exact volume. That means we have to do the double integral, right, which is the limit of that double sum. Well, that means we have to integrate the function we want the volume underneath, right? This is a non-negative function, so we don't take minus the double integral, right? We take plus the double integral at volume below a non-negative surface. By Fubini's theorem, that's equal to the iterated integral. X going from its minimum to maximum, 0 to 1. Y going from its min to max, minus pi over 2 to pi over 2. F of xy, the surface we want the volume underneath, dy dx. So there's Fubini's theorem for this one, and we can calculate the volume exactly for this one. What we can do is this. This is a real help in some of the problems, actually. If you think about it, this inside integral is a partial integral treating x as a constant. So within this integral, e to the x is e to a constant is a constant. You can pull it out, right? So you can put the e to the x out here. Now once the e to the x is outside the integral that's left, from minus pi over 2 to pi over 2 of cosine y dy, that's an integral plug-in constant endpoints. This is just a number, right? Integral cosine y dy from minus pi over 2 to pi over 2 is going to be a number. So we can pull this whole integral outside. So what we do is we pull e to the x out here, and then the rest of the integral we pull out here, and we've got rewritten this as the product of two integrals. You can only do this when it's a function of x times a function of y, right, between constant endpoints. You just have to think about it. I can pull a constant out is all I'm saying. So I'll pull the e to the x out here, and then pull this integral sign through here, or the dx through here, whichever way you like to think about it, and write this as a product of two integrals. Integral from 0 to 1, e to the x dx, integral from minus pi over 2 to pi over 2, cosine y dy. These are easy integrals, right? Integral of e to the x. Well, let's do one thing first. Here's another principle that applies sometimes. Cosine y is an even function over a symmetric integral. Minus a to a is always twice the integral from 0 to a, right? We know that for any even function. So I'm going to rewrite integral cosine y from minus pi over 2 to pi over 2 as twice the integral from 0 to pi over 2. All right? That'll make my evaluation a little easier, maybe. And now integral of e to the x is e to the x. I have to plug in the endpoints and take the difference. Integral cosine y is sine y. I have to plug in the endpoints and take the difference. These two integrals are just 1. This one's e minus 1, and this one's 1. And so I get twice e minus 1, or 2e minus 2 is the value of this double integral, and hence the volume below the surface, z equals e to the x cosine y above this rectangle. Let's try another one, I'm thinking. Suppose I wanted to do this. Suppose I wanted to find the value of the double integral over the rectangle of x minus y dA. This one is not necessarily a volume, because this isn't necessarily positive over the whole, non-negative over the whole region. Suppose R is the rectangle, the set of all x, y. Here's the other notation we can use, is this set builder notation. Set of all x, y such that, let's say 0 is less than or equal to x is less than or equal to 1, and 0 is less than or equal to y is less than or equal to 2. What is this double integral? By Fubini's theorem, we can write this as integral x going from 0 to 1, its min to max, integral y going from 0 to 2, its min to max, x minus y dy dx. This variable has to go with its endpoints on the inside, and this variable with its endpoints on the outside. And now, how can we evaluate this? We can't break it up as a product of two integrals. We just have to integrate directly. So let's say this is the integral from 0 to 1, and now this integral is a partial integral treating x as a constant. So think of integrating c minus y. What's its integral? cy minus 1/2 y squared, but c is x. So this is xy minus 1/2 y squared. Partial integration of x minus y. Then I have to plug in endpoints 0 and 2 for y, and then finally integrate with respect to x. Right? So there's going to be the value of this integral. Let's bring it back up here. Now you plug in y equals 2, and you get 2x minus 2. Right? And then you plug in y equals 0, and you get nothing. And so I'm left with this integral. Plug in the top endpoint, you get this. Plug in the bottom endpoint, you get 0. Their subtraction is this. Well, now this is just a calculus 1 integral, and so I say integral of 2x is x squared. Integral of 2 is 2x. I need to just plug in 0 and 1 and take the difference. This is 1 minus 2 is negative 1. We got negative because the surface now dips below the xy plane, and we're getting volume below the xy plane in that case. Okay, so let's bring this back up now. That's interesting for integrating below a surface over a rectangle. Don't we want to do something more complicated than that, though? We do. For a non-rectangular region R, what are we going to do? Right? A double integral over a region R that's non-rectangular, we're going to define it, def, this way. We're going to take the limit as the number of subrectangles over the region goes to infinity of the sum k equals 1 to n, j equals 1 to m again. Instead of f of x j star y k star, we're going to take f hat of x j star y k star times delta x j delta y k as before. It's the same thing as before for its look, but f hat is this, and the limit of the sum is not over a rectangle, it's over the original rectangle for the domain of the function, it's over a big rectangle that encloses the region. So if I have a closed bounded region over which a surface sits here, z equals f of x, y, and I want to estimate the volume below that surface over a non-rectangular region, I enclose it with my favorite rectangle, and then I partition the x and y axis in the same way, and I integrate over this enclosing rectangle, not the original function, but the function f hat that's equal to the original function of x, y is in the region R, the non-rectangular region, and 0 if it's elsewhere in the rectangle. And so what I'll do, you can kind of see it here, I'll take a rectangular box of height 0 if the point I pick for the height of the function is outside the domain of the original function, because f hat will be 0. But if I'm inside the domain of the original function, I'll go up to the height of the surface and take a rectangular parallel pipe, a rectangular box of the height of the surface at that point. And so I'll add up rectangular boxes over the surface, under the surface, and then add up zeros outside here. And it turns out, in the limit as the number of rectangular subregions goes to infinity with the width of the widest in each direction going to 0. For nice regions like simple closed curves, or what we're going to call type 1 and type 2 regions, this limit of this sum is the same regardless of those partitions and regardless of the points xj star, yk star I pick inside. So we'll just define this to be the double integral of a function over a non-rectangular region. And then we can use this to evaluate volumes below a surface and over other regions. For instance, suppose f is continuous over what's called a vertically simple region. That means it has vertical lines on each side, x equals a, x equals b, but on the bottom and top you can have functions, y equals g1 of x, y equals g2 of x, that are continuous with g1 less than or equal to g2, so they don't cross. Right? Or you can have a horizontally simple region. You have two horizontal lines, y equals c and y equals d, in a left curve, x equals g1 of y and x equals g2 of y, and a region with, it should say g1 of y less than or equal to g2 of y here, continuous. then the double integral exists and is equal to the iterated integral, where you go, in the first case, x going from a to b between the vertical lines, but y goes between the bottom function g1 of x and the top function g2 of x, two functions of x. Or, if it's a horizontally simple region, you can go between y going from this bin to x max, x going from a left curve g1 of y to a right curve x equals g2 of y. A good way to figure out which one's on the left and right is just draw a horizontal line. And whichever one it intersects at the smaller x value is on the left, whichever one it intersects at the larger x value is on the right. And so that's how you decide which ones to put in the integral. You let y go from its min to its max, c to d, and x goes between variable functions that are functions of y, right? g1 of y and g2 of y. And the theorem says that for these vertically simple and horizontally simple regions, the double integral exists, the volume under the surface exists over this non-rectangular region, and it's these kinds of iterated integrals where the inside integrals are functions of x or y, respectively. Here's the last example. Suppose I want to find the volume below the plane z equals x plus y, right? This is going to be a non-negative function, so this will be the volume under the plane. And suppose it's over this rectangle in the xy plane, right? X going from 0 to 2 and y going from 0 to 1. Well, the volume by our definition there is now the double integral over the rectangle, the triangle, x plus y dA, the height of the surface. And by our theorem we just wrote, for a vertically simple region, if I treat this as vertically simple, vertical line on the left, think of this point as a vertical line on the right. X goes from 0 to 2, so that's the outside one. But the inside one, y goes from a function of x, 0, to a function of x. Well, it's a line. If you think about it, its y-intercept is 1, and its slope, it goes down 1 over 2 with minus a half. So y equals mx plus b, with m equals minus a half and b equals 1 gives you the equation of the line. There's the top bounding line. And so we have to integrate from the bottom curve, y equals 0, to the top curve, y equals 1 minus a half x, the equation of the line, the height of the surface. So integral x going from min to max, y goes from bottom curve to top curve, integral the height of the surface dy dx. Well, we could do this in the same fashion as the last one, right? We evaluate the inside integral treating x as a constant. Integral of x is xy, because x is treated as a constant. Integral of y, however, is 1/2 y squared. Y is not treated as a constant. We have to plug in 0 and 1 minus a half x, the equation of the line here, in the different lines. And when we plug those in, we get this. And this is a calculus 1 integral to do, right? We just simplified. I grouped the like terms here. I have to integrate 1/2 plus a half x minus 3/8 x squared from 0 to 2. That's easy. Just take the antiderivatives, fundamental theorem of calculus. Here's the antiderivative, plug in 0 and 2, take the difference. It comes out to be 1. This actually has unit volume over the triangle here. And that completes the material for today.